Alright, this is a musical instrument I'm working on. It's electronic. It's going to have circuitry inside. Here's the circuitry so far. There's a 14-bit serial DAC board which goes to an audio amplifier board, which is green, and the 14-bit DAC is driven by a programmable, field programmable gate array, a programmable logic chip. It's called, anyway, got some batteries. Right now the FPGA needs to be powered off of USB. The audio amp drives this coil, which came from SparkFun Electronics. The coil basically imparts momentum to the wood that it's attached to. So it's attached with some nuts and bolts to this backboard of the instrument. These bolts are a keyboard which is not yet connected. So right now it plays a tune that I just programmed the FPGA with. So now I'm going to demonstrate the whole thing together playing the tune. There's all the pieces connected together. This is a simple 1-4-5-1 progression that I put together. Since I can't yet play the thing with the keyboard, I did this instead. So that's that. Maybe not terribly exciting, but you can hear that there's a little bit of there are chords in there. It has 3 voices. I'm going to pause, get rid of that now. So here's what's going on inside the FPGA. We have 3 voices. Each voice has a linear envelope, triangle wave. We feed a frequency to the triangle wave generator, and we hit the envelope generator with a signal to start the note. We multiply those two to give us the envelope that makes the note shrink over time. Takes about a half a second. We add together that with 2 other voices that are playing different frequencies. That goes to a circuit that drives the 14-bit serial DAC. The process for development is I start writing in Python code. Each of these little blocks is a piece of Python code. I use something called myHDL, which converts that to Verilog, which is a standard language for designing chips. Then I run that through Xilinx design tools to produce a bit file which programs the FPGA. That bit file gets programmed into the board, and that makes the FPGA do that. And there's some other circuitry to provide the frequencies and the signals to start the notes. I haven't shown that here, but obviously that's necessary for it to work, and that's where the tune is stored and that stuff. Next thing is the keyboard. So I have all these nuts and bolts on here. These are 1024 nuts and bolts. The silvery ones are the white notes on the piano keyboard. The brass ones are the black notes on the piano keyboard. The keyboard is kind of folded, so you don't have to stretch your fingers as far as you would on a piano. They are going to be touch sensitive, and the touch sensitivity works like this. We take each of those. So we have a big switch so that we're only looking at one machine screw at a time. That machine screw gets used in this 555 timer circuit. Let's zoom out a little bit. So that translates. So we apply the bits to select one of the machine screws, and then we apply a very short low pulse to the trigger input of the 555. We get a pulse width on the output of the 555, and in preliminary experiments that varies between, oh, let's see, about 1 microsecond pulse width if I'm not touching the bolt, and 10 or 15 if I'm really pushing hard on the bolt. So that means that I can get a pulse width that varies with how hard I'm touching the bolt, and that means that it isn't just are you touching or not, it's also how hard are you touching, or did you bang on it, or did you just daintily touch it. So I can get a pianoforte by looking at that pulse width. So looking at that pulse width is going to be done by circuitry in the FPGA, which is on this red board that right now is upside down. And then I'm also going to use, this is a BeagleBone Black, which is a microcontroller board that is costs about $45. Excuse my spastic camera work, but right. So that's a popular board. It's similar to a Raspberry Pi, except that it has many more GPIO pins. But other than that, it's pretty similar to a Raspberry Pi. So that's going to be another piece, and that's going to provide all the smarts that I need to run the thing. So basically, it will take the scanned keyboard and convert that to the frequencies that are then fed back into the... So the scanning is done in the FPGA. That information gets loaded into the BeagleBone Blackboard, gets translated into frequencies. Those go back into the FPGA. And you might wonder, why would I bother with that? Why don't I just why don't I just do everything in the FPGA? The reason I'm interested in doing that is because if you look back at, this circuit here, this is the circuit for the voice. I can actually have a lot more flexibility if I design some more modules and I use the BeagleBone Black to choose between them. Also, there will be other things. There will be other effects, maybe some echo effects, other stuff that I'll want to control, and it'll make the instrument just generally more flexible and programmable. So that's where things are at right now, and as I demonstrated briefly ago, the current state of where it's at is that it plays that tune. So that's what's going on. All right. Thanks for watching.